Acid-base reactions. Acids and bases are as familiar as aspirin and milk of magnesia, although many people don't know their chemical names. Acetic acid, it's aspirin, and magnesium hydroxide, it's a milk of magnesia. In addition to being the basis of many medicinal and household products, acid-base chemistry is important in industrial processes and essential in sustaining biological systems. Before we can discuss acid-base reactions, we need to know more about acids and bases themselves. We can define acids as substances that ionize in water to produce H+ ions, and bases as substances that ionize in water to produce OH- ions. These definitions were formulated in the late 19th century by the Swedish chemist Arrhenius to classify substances whose properties in aqueous solutions were well known. Arrhenius's definitions of acids and bases are limited in that they apply only to aqueous solutions. Broader definitions were produced by the Danish chemist Brønsted in 1932. Brønsted acid is a proton donor and Brønsted base is a proton acceptor. Note that Brønsted's definitions don't require acids and bases to be in aqueous solutions. Hydrochloric acid, for example, is a Brønsted acid because it donates a proton in water. You can see it in this reaction. Acids commonly used in the laboratory include hydrochloric acid, nitric acid, also in this slide acetic acid, sulfuric acid, phosphoric acid, and other acids. The first three are monoprotic acids. Hydrochloric acid, nitric, and acetic acids. As mentioned earlier, because the ionization of acetic acid is incomplete, you can see double arrows. It's a weak electrolyte. For this reason, it's called a weak acid. On the other hand, hydrochloric acid and nitric acid are strong acids because they're strong electrolytes. So they are completely ionized in solution. So you can see the single arrow, only one route. Sulfuric acid is a diprotic acid because each unit of the acid gives up 2 H+ ions and 2 separate steps. Sulfuric acid is a strong electrolyte or strong acid. The first step of ionization is complete, but second step for the second step, sulfuric acid is a weak acid. Not so weak, but maybe medium acid, because it's a weak electrolyte, and we need a double arrow to represent its incomplete ionization. Triprotic acids, which yield 3 H+ ions, are relatively few in number. The best known triprotic acid is the phosphoric acid. You can see these ionizations, all 3 steps. All 3 species in this case are weak acids, and we use the double arrows to represent each ionization step. Anions such as H2PO4- and HPO4 2- are found in aqueous solutions of phosphates such as sodium phosphate, various sodium phosphates. In this slide, you can see some of strong acids and some of weak acids. Sodium hydroxide and barium hydroxide are strong electrolytes. This means they are completely ionized in solution. The OH minus ion can accept a proton through these equations. Thus, OH minus is a Bronsted base. Ammonia is classified as a Bronsted base because it can accept H plus ion. You can see. Ammonia is a weak electrolyte and therefore a weak base because only a small fraction of dissolved ammonia molecules react with water to form NH4 plus and OH minus ions. The most commonly used strong base in the laboratory is sodium hydroxide. It's cheap and soluble. The most commonly used weak base is the aqueous ammonia solution, which is sometimes erroneously called ammonium hydroxide. There is no evidence that the species of ammonium hydroxide actually exist other than the NH4 plus and OH minus ions in solution. So it's not so right to write in bottle the solution of ammonium hydroxide. All of the groups first A and second A elements form hydroxides, and particularly all these hydroxides is strong bases. It's not only beryllium hydroxide is not strong base. Our hydroxides is strong bases. A neutralization reaction is a reaction between an acid and a base. Generally, aqueous acid-base reactions produce water and salt, which is an ionic compound made up of a cation other than H plus and an anion other than OH minus or O2 minus. For example, when hydrochloric acid solution is mixed with sodium hydroxide solution, the following reaction occurs. This one. However, because both the acid and the base are strong electrolytes, they are completely ionized in solution. The ionic equation is this one. It's a long ionic equation, but if we cancel sodium and chloride anions, we leave only H plus, OH minus, and water. It's a short way to write the ionic equation. Now consider the reaction between sodium hydroxide solution with hydrocyanic acid, which is a weak acid. This one. In this case, the ionic equation is this one, but in this equation we can cancel only sodium cations. And the short way to write the ionic equation is this one. The following examples of acid-base neutralization reaction represented only by molecular reactions. I think all of you can write more reactions because we already know many acids and bases, and all reactions between acids and bases will be neutralization reactions. Certain salts like carbonates, bicarbonates, sulfites, and sulfides, react with acids to form gaseous products. For example, the molecular equation for the reaction between sodium carbonate and hydrochloric acid. Carbonic acid is unstable, and if present in solution in sufficient concentrations, decomposes to water and carbon dioxide. In this slide, you can see additional reactions with gaseous products. For example, reaction with sodium bicarbonate, sodium sulfide, potassium sulfide, and with gaseous products. Water functions as a base in reactions with acids such as hydrochloric acid and acetic acid, and it functions as an acid in reactions with bases such as ammonia, for example. Water is a weak, very weak electrolyte, and therefore a pure conductor of electricity, but it does undergo ionization to a small extent. This reaction is sometimes called the auto-ionization of water. To describe the acid-base properties of water in the Bronsted framework, we express its auto-ionization as follow these equations, or in this short way. The acid-base conjugate pairs are water as acid and OH minus hydroxide as a base, and with cation hydroxonium as acid, and water as a base. In the study of acid-base reactions, the hydrogen ion concentration is a key. Its value indicates the acidity or basicity of the solution, because only a very small fraction of water molecules are ionized, the concentration of water remains virtually unchanged. Therefore, the equilibrium constant for the auto-ionization of water is this one. Because we use H plus and H3O plus interchangeably to represent the hydrated proton, the equilibrium constant can also be expressed like this. To indicate that the equilibrium constant refers to the auto-ionization of water, we can replace this K to this K of, like K of water. It can be called the ion product constant, which is a product of the molar concentration of H plus and OH minus ions at a particular temperature. In pure water at 35 centigrade, the concentrations of H plus and OH minus ions are equal and found to be 1 multiplied by 10 under the power of -5, and the same concentration of OH minus. So the constant will be 1 multiplied by 10 under the power of -14. It's a constant of water. Whenever we have pure water or an aqueous solution of dissolved species, the following relationship always hold at 25 Celsius degree. Whenever concentrations of H plus and OH minus is equal, the aqueous solution is said to be neutral. In an acidic solution, there is a excess of H plus ions, and in base solutions, there is a excess or amount of hydroxide ions. In practice, we can change the concentrations of H plus or H minus in solution, but we cannot vary both of them independently. If we adjust the solution so that, for example, concentration of H plus is 1 multiplied by 10 under the power of -6, the concentration of OH minus ions, we can calculate it by using this equation, and it will be 1 multiplied by 10 under the power of -8 moles. Because the concentrations of H plus and OH minus ions in aqueous solutions are frequently very small numbers, and therefore inconvenient to work with, a more practical measure called pH was proposed. The pH of a solution is defined as the negative logarithm of the hydrogen ion concentration. This is the formula. Keep in mind that equation is simply a definition designed to give us convenient numbers to work with. The negative logarithm gives us a positive number of pH, which otherwise would be negative due to the small values of H plus, concentration of H plus. Furthermore, the term concentration of H plus pertain only to the numerical part of the expression for hydrogen ion concentration, for we cannot take the logarithm of units. Thus, like the equilibrium constant, the pH of the solution is dimensionless quantity. Because pH is simply a way to express hydrogen ion concentration, acidic and basidic solutions at 25 Celsius degree can be distinguished by their pH values as follow. For example, this slide, you can see if pH is less than 7 is acidic solution. If pH is more than 7 is basic solution, and neutral solution is when pH is exactly 7. Notice that pH increases as H plus concentration of H plus ions decreases. Sometimes we may be given the pH value of a solution and ask it to calculate H plus ion concentration. In that case, we need to take the antilog of equation as follow these formulas. Be aware that the concentration of pH just shown and indeed all the calculations involving solution concentrations. In reality, ion pair formation and other types of intermolecular interactions may affect the actual concentrations of species in solution. The actual or effective concentration of a solute may not be that we think it is, knowing the amount of substance originally dissolved in solution. One way is to replace the concentration term with activity, which is the effective concentration. Strictly speaking, then the pH of solution should be defined as this one. A pOH scale analogous to the pH scale can be devised using the negative logarithm of the hydroxide ion concentration of a solution. Thus, we define pOH as this formula. You can express it like this and calculate OH minus like this. Now, consider again the ion product constant for water at 25 degree is this one. And from definition of pH and pOH, we obtain that sum of pH and pOH is exactly 14. Equation provides us with another way to express the relationship between the H plus ion concentration and the OH minus ion concentration. In modern chemistry, you can use various pH meters to measure pH of various solutions. In this slide, you can see one of the examples of pH meters that we can use in our laboratory.